CRESST, Cryogenic Rare Event Search with Superconducting Thermometers. Only a small fraction of the universe is made up of stars, planets, and black holes. A by far larger component probably is the so-called dark matter. Strong evidence for the existence of dark matter was, among other things, gained from measurements of rotation velocities of stars in spiral galaxies. Today, high-precision measurements of the cosmic microwave background provide a detailed knowledge of the composition of the universe. According to these observations, there is roughly 5 times more dark matter than ordinary matter. However, up to now, it remains unclear what dark matter is made of. The world's largest underground laboratory houses CRESST, an experiment designed to investigate the nature of dark matter. The currently most favored explanation for dark matter is the existence of a previously unobserved elementary particle, known as Weakly Interacting Massive Particle, WIMP. CRESST aims to directly detect WIMPs via their interactions with the detector. CRESST is surrounded by 1,400 meters of rock in all directions to minimize disturbing cosmic rays. The probability of a WIMP to interact with the rock is extremely low. Therefore, the fraction of WIMPs stopped in the rock is negligible, and most of the WIMPs reach the detector undisturbed. Natural radioactive decays in the rock and the experimental material itself make up for the remaining background radiation in the Gran Sasso laboratory. Several layers of shielding, made of different materials, protect the detectors against this background radiation. The CRESST apparatus has room for 33 modules. The core component of each module is a calcium tungstate crystal with a mass of 300 grams. The experiment is protected against its surrounding by the shielding. CRESST detectors are supersensitive particle detectors expected to observe no more than 1 WIMP per week. However, in the same period, a few thousand well-known particles, like for example electrons, are measured. Every particle interacting in the crystal produces heat and scintillation light through a scattering process in the crystal material. The warming of the crystal is registered by the thermometer on the bottom of the crystal. The energy deposited in the crystal by the scattering process can be derived from the measurement of this temperature rise. The scintillation light leaving the crystal is captured inside the module by a reflective housing and is absorbed by a silicon disc which warms up. The temperature increase of the disc is measured with a second thermometer. The determination of such small energies requires low temperatures in the order of 10 millikelvin above the absolute zero point of -273.15 degrees Celsius. The amount of scintillation light produced depends on the type of particle. Thus, by measuring the light, discrimination between different particles is possible. If the hunt for WIMP-like dark matter succeeds, astronomy and particle physics, the physics of the very large and the very small, will once more complement each other and allow for a deep insight into the nature of the universe.